The planet K2-18b has been hitting the headlines again this month with the claim of a tentative detection of something known as dimethyl sulfide in its atmosphere, a molecule which is only produced by life here on Earth. Now, this is all thanks to this research paper by Madhusudhan and collaborators. And if you want a deeper dive into all of this with more context and caveats than you're gonna get in the wider media, then you are in the right place. So let me be clear early on. No, we have not detected alien life in this planet's atmosphere. The detection itself is tentative, and the molecule itself of dimethyl sulfide doesn't necessarily mean that life is present. This whole story is quite literally the definition of extraordinary claims require extraordinary evidence. We don't have that yet. Now, if you're thinking, haven't I heard this all before? Well, technically, yes. The same research group put out this paper in 2023, claiming an even more tentative detection of dimethyl sulfide. And I made a video about that then, but the data they had at the time from the James Webb Space Telescope wasn't good enough for them to make a strong claim. So now they've got different data from the James Webb Space Telescope, and they're claiming that they do now have stronger evidence. But if you've been following me for a while, then you know that all of this hype around K2-18b comes with a lot of scientific debate, with other research papers claiming there's no evidence for dimethyl sulfide in K2-18b's atmosphere at all. And this past week or so, since this new research paper with this new claim to have evidence of dimethyl sulfide dropped, has been no exception, because already, within the space of a week, another research paper was published by Taylor, refitting this new JWST data and claiming there's no evidence for dimethyl sulfide. I was actually lucky enough to be at a conference in Oxford this week where there was actually a panel discussion between Madhusudhan and Taylor, the two lead authors on these papers, discussing these results. This is science in action, and it is incredibly exciting to get to live through all of this debate as we try and figure out what's going on. So in this video, I'm going to try and distill all of that for you, and we're going to chat first about the planet K2-18b and what we already know about it. Then, second, what Madhusudhan and collaborators have claimed to have found. Third, how strong their evidence now is for this detection of dimethyl sulfide. And finally, the counter-arguments to this detection. Now, I know discussing the possibility of whether there's life out there in the universe can be, just a bit scary for some, because let's face it, there's just an existential crisis waiting to happen that we can't protect ourselves from. But you know what's even scarier than that? The internet. And thankfully, you can protect yourself while you're online thanks to Surfshark, the sponsor of this week's video. Surfshark is a VPN, a virtual private network, and it's essentially a middleman between your computer and the scary internet, which means your private information, your location, and what you're doing is all hidden from anybody who happens to be snooping. Surfshark is crucial for me, especially with my life as an academic, because I'm always working on public Wi-Fi networks, whether that's in my office, in the university library perhaps, or when traveling for work. It means that, no one can snoop on my credit card information, but also my unreleased research paper and steal all of my ideas. Plus, Surfshark helps you get the best price when online shopping, so websites usually show you prices based on your location, especially when it comes to things like flight prices. Surfshark helps you get the best deals, which means I can make the most out of my very small research travel budget. I also love that Surfshark has an antivirus software that shields my device from viruses, malware, and ad tracking. Look, there's no risk in trying Surfshark because they offer a 30-day money-back guarantee. So why don't you try them out today by heading to surfshark.com/Dr. Becky, or you can click on that link in the description below, or you can use code Dr. Becky at checkout and you'll get 4 additional months free on your subscription, which is a great deal for you all. So a big thanks to Surfshark again for sponsoring this video. And now let's dive in and chat first about the planet K2-18b and what we already know about it to kick us off. So K2-18b is what's known as an exoplanet, a planet orbiting another star in our galaxy of stars, the Milky Way. It's about 124 light years away from Earth in the constellation of Leo, and it was discovered in 2015 by NASA's Kepler Space Telescope during its K2 mission, hence the name. Now it orbits a red dwarf star which is much smaller and cooler than our sun. K2-18b actually only takes 33 days to make one orbit of its star. So it orbits much closer to its star than Earth does around the sun, but because its star is much cooler than the sun, it's still in what's known as the habitable zone around its star, where you're getting, just the right amount of light, so heat and energy from a star, so that any planet there wouldn't be, too hot or too cold for life to potentially exist there, at least life as we know it here on Earth. Now, it was back in 2019 that K2-18b hit the headlines for the first time when Becky and collaborators using the Hubble Space Telescope claimed to have found evidence for water vapor in its atmosphere, which was a huge deal at the time. Yeah, we'd found water vapor in the atmospheres of exoplanets before that, but we never found it in the atmosphere of an exoplanet in its habitable zone around its star. So that right there already had people speculating about the possibility of life on K2-18b. That's despite the fact that Coulter and collaborators had already worked out the mass of K2-18b as 8.63 times heavier than Earth, but with a diameter of just 2.6 times that of Earth, putting its size roughly about halfway between Earth and Neptune. So that had people asking, well, what is K2-18b actually like then? Is it more of a super Earth, with a rocky surface and maybe even like a liquid water ocean? Or is it more of a mini Neptune, like the gas giants with no surface at all and just gas all the way down? In fact, there are a lot of planets that have been found through the 2010s in this region between Earth and Neptune, just like K2-18b. And we don't have anything like that in the solar system to help inform us, okay, what do we expect to find? So the focus was very much on understanding, okay, what are these planets actually like? So, at the end of the 2010s, with the James Webb Space Telescope launch still a few years off, Hugh and collaborators started to make predictions for what you might expect to find with JWST. If it was a super Earth with a liquid ocean, then carbon dioxide and nitrogen should dominate in the atmosphere. But if it was a mini Neptune, like a mini gas giant, then ammonia and methane would dominate. And so this is what motivated two separate groups to apply to use JWST to observe K2-18b to figure out which one it was. So how do you actually do this with JWST? Well, first you have to wait for the planet to pass in front of its star from our perspective here on Earth, so that a tiny bit of starlight passes through the planet's atmosphere. You can then take that light and split it into what's known as a spectrum, where you get a trace of how much light at each colour or wavelength you have. And then you take the spectrum of just the starlight alone, take one from the other, and you're left with just the effect of the planet's atmosphere. So if there are certain molecules in the atmosphere of the planet, they'll absorb specific wavelengths that are signatures of those molecules. And you can identify them as gaps or dips in the amount of light detected to know that they're there. And sometimes when people plot this, instead of plotting like amount of light detected, they actually plot like amount of light absorbed. So the axis essentially gets flipped. And so instead of a dip to show you where the individual molecules are, instead you get a bump in the spectrum instead. Now, I made that sound relatively simple, but in reality, it's an incredibly difficult thing to do. Mainly because the amount of light that actually passes through the planet's atmosphere is absolutely minuscule. So only the strongest features tend to show up above the noise. So what people often do is observe multiple transits of the planet in front of its star, and then you can add the light from all of those different transits together to get a stronger signal. But the big problem with that is that you have to assume that the light from your star is relatively constant and won't change from transit to transit, whether that's every 33 days like for K2-18b or, year on year if it's a planet like Earth, which, as we know from observing our own sun, is just not the case. From sunspots to flares to just general convection, stars are naturally variable, with sunspots actually able to change the amount of light given off at specific wavelengths as well. So astronomers tend to approach doing this with a lot of caution and with a lot of caveats in mind as they present their work. So With all of that said, that brings us to 2023, when Madhusudhan and collaborators published the first look at K2-18b with JWST, but using the near-spec and NIRISS instruments that cover the lower wavelengths of infrared light. I already covered this specific research paper in a video on my channel when it first came out, which I'll link that below if you're interested in a big deeper dive onto that paper, because obviously I go into way more detail there. But to summarize, by fitting to that JWST data, Madhusudhan and collaborators find that their best fit model gave a mix of molecules of hydrogen and methane, which supported the idea that K2-18b is what's known as a Haitian world, a portmanteau of hydrogen and ocean, blending this idea of a super Earth and a mini Neptune. So it's a liquid water ocean surface surrounded by a thick hydrogen atmosphere, like what the gas giants have, but just, not quite as thick. But the result from that paper that got the most attention was this tentative claim of the detection of a molecule called dimethyl sulfide, which is what's known as a biosignature, a signature of life, a signature of biochemistry producing that molecule in a planet's atmosphere. And the reason that dimethyl sulfide is linked in that way is because here on Earth, the only thing that we know of to produce dimethyl sulfide is microbial life. It is biochemistry. Now, this was tentative because it was an incredibly weak detection, with a 1 in 66 chance that what they found was a statistical fluke due to noise in their data. For context, in physics, we like those odds to be less than a 1 in 3.5 million chance before we're sure of a detection. And one of the reasons that that evidence was so weak was that signature of the amount of light absorbed by the atmosphere by dimethyl sulfide, that bump there, was in the same place as a signature you expect from methane. Plus, as I've also covered in another video on my channel before, there's been many challenges to that claim, with people finding different best fit models to that exact same data. For example, Wogan and collaborators point out that a mini Neptune gas atmosphere all the way down with no surface is equally as likely as a model as the Haitian world with dimethyl sulfide in its atmosphere. Whereas Shortall and collaborators claim that while yes, K2-18b does seem to have a very thick hydrogen-dominated atmosphere, instead of being over a liquid water ocean though, it's over a magma ocean, and they find no evidence for dimethyl sulfide. There's also been this work from Schmidt and collaborators that was released just a few months ago, who reanalyzed again the same JWST data with 60 different codes that take the transit data and pull out the impact from the atmosphere, and 250 different codes that then fit a model of the atmosphere to the data. And with all of those, they say they do find a 4 sigma detection of methane, but no evidence for dimethyl sulfide or carbon dioxide, and instead say that K2-18b is most likely a mini Neptune, with no liquid water ocean and no life in the atmosphere needed to explain the data from JWST. And if you watched my previous video going through these different claims, you'll know that at the end I talked about, okay, well, how are we going to actually figure out what's going on here? And I said this. More JWST data is going to help here, specifically from the MIRI instrument on board JWST that goes to much longer wavelengths than NIRSpec. Which brings me to part 2, what Madhusudhan and collaborators have claimed to have found, this time using the MIRI instrument on board JWST, which looks at the much longer wavelengths of infrared light. And this data is crucial if you want to find out if there is actually dimethyl sulfide in the atmosphere of K2-18b. Because unlike at lower wavelengths, where that bump from dimethyl sulfide is in the same place as the bump from methane, at longer wavelengths, there's a few different bumps solely from dimethyl sulfide and dimethyl disulfide, both of which here on Earth are biosignatures. They are only produced by life. So, with MIRI data from JWST, Madhusudhan and collaborators wanted to see if there was any stronger evidence for dimethyl sulfide at these wavelengths. Now, they took that data back in April 2024 over 6 hours with just a single transit of K2-18b in front of its star. They did the whole comparison of before and after the transit, taking the light of the star away to isolate just the impact of the atmosphere, and here's what they found. So the horizontal axis here is the wavelength of light detected, and the vertical axis is the amount of light absorbed. The browny reddish points are the data they got from JWST, and they have the error bars there showing how uncertain that measurement is. Generally speaking, like the bigger the error bar, the more noise you have in your data. The blue line is their best fit model atmosphere to the data, with the blue shaded regions once again showing the uncertainty on that. Then the yellow points is like they've observed the blue line with JWST and got out the points at the same wavelengths as the brown data points. Essentially, like the difference between the brown and the yellow helps you see the difference in the data to the model and whether the model predictions fall outside of those uncertainties on the data, outside of those error bars. And if you compare this spectrum with like a lab spectrum of where we expect to see those signatures of dimethyl sulfide and dimethyl disulfide, you find that, yeah, the bumps in the data are sort of there in the places that you'd expect them to be given what we observe in the lab. So by looking at this by eye, maybe you're like, yeah, okay, that seems like a detection of dimethyl sulfide. But we can do better by just looking at it by eye. We can do some statistics. Which brings me to part 3, how strong their evidence is for a detection of dimethyl sulfide. So with statistics, we can quantify that difference between the best fit model and the data, between the brown and the yellow points on this plot, to say whether the bumps in the model that come from the dimethyl sulfide can explain the wiggles in the data or if it's just noise. Essentially, how sure are Madhusudhan and collaborators that a model with dimethyl sulfide and dimethyl disulfide is the correct one for K2-18b? So here's a big table with all the different codes and tests they ran with different models. Some that just have dimethyl sulfide in the atmosphere, some with just dimethyl disulfide in the atmosphere, and some with both of them. And the numbers to look at here are the ones in the final 3 columns. And essentially, the bigger the number, the stronger the evidence is for a given model. And in the final column, what you've got here is how much more likely their model is over just a flat line fit to the data. And so you can see in the basic models, they find around about a 3 sigma detection significance. That translates to a 1 in 370 chance that their detection is just a statistical fluke. Now that is up from the 2.4 sigma detection they had last time, the 1 in 66 chance. But it's still not quite that 5 sigma threshold, that 1 in 3.5 million chance that it is just a fluke in the data due to noise that we usually take as that sort of threshold for saying we have definitely detected this. Now, to be fair, in astronomy, we tend to be slightly laxer with that detection limit, and usually people will take 3 sigma as like a over 3 sigma, we're pretty sure of a detection. For example, if we go back to 2019 and Becky and collaborators' claim of water vapor in the atmosphere of K2-18b, that was a 3.93 sigma result. But extraordinary claims require extraordinary evidence. So with that in mind, Madhusudhan and collaborators spent a long time essentially trying to break their results, trying to get rid of the dimethyl sulfide, thinking of some other way that you could account for that bump that wasn't to do with dimethyl sulfide in the atmosphere. Whether that's, considering all the systematic issues that could have gone wrong in the analysis or something in the data that added some sort of bias. But even then, they still found around a 3 sigma significant detection of dimethyl sulfide. But what about these other 2 columns in the table? These are what's known as the Bayesian evidence for a model. Now, this is a much more rigorous statistical test that you can do, and people tend to trust these numbers more. And like I said, like the bigger the number, the more evidence you have for a model. But they're most useful when you're comparing the Bayesian evidence for one model to the next. You look at the difference, or what's known as the delta. Like, for example, comparing a model with dimethyl sulfide and one without dimethyl sulfide that is just a flat line, for example. But here in this table, we're just comparing, like, is there dimethyl sulfide or dimethyl disulfide, or maybe both together in a model. There's no comparison to the flat line model like what's given in the column on the right. Which brings me to part 4, the counter arguments against this. So we already heard in the earlier part of the video about the claims from Shortall and collaborators, Wogan and collaborators, and Schmidt and collaborators that reanalyzed the previous set of data from NEARSPEC and NIRIS on JWST that was released 18 months ago. But what about a reanalysis of this new JWST data from MIRI? Well, amazingly enough, despite it being only a week since this first research paper by Madhusudhan and collaborators come out with this new claim of a detection, there has already been another research paper appeared that refits the MIRI data that was written by my colleague Jake Taylor. You might recognize him from an earlier video of mine where I actually interviewed him about his previous JWST exoplanet atmosphere results. Now, what Taylor has done in this research paper is really interesting because they've essentially said, let's not assume we know anything about the atmosphere of K2-18b. We're not even going to try and fit the data with like a proper physical atmospheric model. We're just going to try and fit it with incredibly simple models. So yes, just a flat line and see what the evidence is for that model, but also for a model just containing Gaussian shapes, which is the shape that absorption features in atmospheres tend to take. It's a really common shape in nature. So here's the exact same MIRI data from JWST for K2-18b that was published by Madhusudhan and collaborators. It's shown here by the white circles and again the error bars showing the noise on the data. The purple line here shows the flat line fit that Taylor has made with then the statistics listed in the top left there. And the key one to focus on in that list is the last one, the Bayesian evidence that is a more robust test of a model. Now the next thing that Taylor did was say, okay, if we allow this flatline model to just add just a single Gaussian somewhere, to be like, maybe there is a molecule that is absorbing some light, just allow it to fit a Gaussian to the data. Does it put a Gaussian in there? And here's what Taylor finds, and the fitting code essentially says, nope, a flat line is still the best thing I can do, as shown by the purple line again there. And again, the key thing to compare here is the difference in these Bayesian evidence numbers. And again, there's like thresholds that we use to interpret these differences in Bayesian evidence numbers between models. So for example, if you've got a difference of less than 1 between two models, that means no evidence to support that one model is better than another. Whereas if you've got a difference in Bayesian evidence of greater than 5, then you've got strong evidence in support of one model over another. And here you can see there's very little difference between the two Bayesian evidence numbers. So no evidence in favor of adding a Gaussian. So the next thing Taylor tried to do was actually force a Gaussian to be at a specific wavelength. In the Madhusudhan and collaborators paper, they show this figure, which highlights the MIRI data points which provide the largest evidence for dimethyl sulfide and dimethyl disulfide. So you can see there's a few around 7 microns that really provide the biggest evidence and a few around 8.8 microns. So here's Taylor's fit if you force the model to try and fit a Gaussian at 7 microns. The model fits something, sure, but the Bayesian evidence difference is still less than 1, meaning there's no evidence to say that that fit is better than just a flat line. And then you can do the same thing for the feature at 8.8 microns and find again, no evidence in support of doing that. And then you can allow the model to fit 2 Gaussians if it wants to in any place, but again, no evidence in support. Or you can fix those 2 Gaussians at 7 and 8.8 microns, and then only then do you fit a model which has a difference in Bayesian evidence of 1.21 compared to the flat line model, which puts it into weak evidence territory. If you want to, you can translate this Bayesian evidence back into like a traditional like sigma value that we usually work with. It's about 2 sigma, or a 1 in 44 chance that this is just a fluke of noise in your data. And that is only if you fix your model to specifically fit those Gaussians at where you think the dimethyl sulfide and dimethyl disulfide features should turn up. Which raises a few red flags. As Taylor puts it, this test suggests that only considering a limited set of absorbers at fixed wavelengths, as done in Madhusudhan et al. 2025's canonical model, inflates the statistical evidence for an atmospheric detection. Basically, by going in and looking for dimethyl sulfide at those wavelengths, you are more likely to find it. What do you think, Pip? Detection or no detection? What are you thinking? Or are you thinking? Okay. Now, in addition to the doubts on the detection itself, all of the hype around this comes from the fact that dimethyl sulfide and dimethyl disulfide are biosignatures here on Earth. They are only produced by life through biochemistry. We do not know of any chemical process that can produce dimethyl sulfide that doesn't involve life. Which is why this molecule was originally identified by Seeger and collaborators as something we should look out for with JWST, because they would be less likely to have false positives and are produced in small quantities. Like other gases that we know are associated with life, like methane, for example, they can also be produced by like geological processes here on Earth, like volcanic eruptions, for example. So if you find methane in incredibly large quantities in an atmosphere, it's much more likely that it's come from like a planet-wide, like geological process than it has from life producing it in small quantities. Which is another reason that people have cast doubt on this dimethyl sulfide claim by Madhusudhan and collaborators, because the abundance of dimethyl sulfide in their models is over 10 parts per million per volume. On Earth, the abundance of dimethyl sulfide is more in the parts per billion per volume. So if dimethyl sulfide did exist in the atmosphere of K2-18b, it is apparently at concentrations of 1,000 times higher than here on Earth, which maybe to me points towards, chemistry on a planet-wide scale and not biochemistry from life. Although Madhusudhan and collaborators do argue that this could be because dimethyl sulfide can accumulate in the atmosphere over time as life produces it. But again, this whole assumption that the existence of dimethyl sulfide must therefore equal life on a planet is a very, very big one, because you know where else dimethyl sulfide has been found? On the comet 67P by the Rosetta mission, which was first reported at the end of 2024 by Hani and collaborators. And also, it's been found on Mars by the Curiosity rover, which was reported by Eigenbroder and collaborators in 2018. Both of those places, 67P and Mars, are a lot closer to home, being in the solar system, and there was no great claims or even tentative claims of finding life on either Mars or 67P when those two research papers came out. In fact, I'd hazard a guess to say that they probably passed you by completely. Plus, this focus on finding dimethyl sulfide comes from the desire to search for life as we know it here on Earth. But what if life out there is not as we know it? What if it's completely different to what we're used to here on Earth? I feel like that needs a whole video in itself on that topic, so if you'd like to see that, let me know down in the comments. But hopefully I've managed to convey how wonderfully messy this field of science actually is and how difficult it is to do, but also brought you along for the journey of all of these scientific debates that continue to rage over keyboards and at conferences. Because this is not going to be an easy one to crack. And I think it really highlights very clearly something that I first heard my colleague Sarah Ballard say. That the extent to which we can know whether life does actually exist out there on a planet somewhere in the universe is probabilistic. If we do ever find strong evidence for a biosignature in an exoplanet atmosphere, it will come with a probability of being a fluke. And with the distances of hundreds of light years involved, we currently don't have the technology to be able to send a spacecraft out there to check, which means that we will never know for sure. And that is just something we're all gonna have to make our peace with. So that had a lot of people asking questions, well, what is K2-18b actually like? Is it either, like a soup of Earth, a soup of Earth, super Earth in the solar system? The solar system? Sounds Irish.